Let's continue with the third lab. So this is what we had done in the previous lab, and we had run this, and we had seen the contents of the assembly language program. Now we have to do some debug, so let's do that. And first of all, the idea behind this particular lab is when you type gcc sum 1 to 9 of C and do dot a dot out, you get an output of sum of numbers from 1 to 100 is 50-50. Same thing is something which you should be getting on a RISC-V compiler as well. Okay, so if you do this, now we have to find out a way to do a dot out kind of thing with the RISC-V compiler, and the command to do that is spike pk and the object file. So this gives you the same output, which verifies that the instructions or the simulations are correct as per expected. Now let's try to debug this one. So what we'll do is we'll open up the object dump of this one, and let's say this is what we get. So for example, now if you want to debug all this thing, we need to open a debugger. So what we'll do is we'll debug in spike -d pk sum, I think that's the command. Yes, so this will open a small debug over here. Now some of the commands which I'm going to explain you directly on this particular spike debugger is, let's say if you want your program counter, which is the PC, to run till this point, and from this point onwards we are going to run manually. So let's do that. The command to do that is until PC 0 to 100B0. That's the memory address location of the first instruction. So it says that your assembly code has run has run all the instructions before 100B0, and from 100B0 is something. Let's debug. So this particular instructions, it is pretty clear. It's going to modify the contents of A2. So before modification, let us try to find out what is the contents of A2. So the contents of A2 are reg 0 A2. That is a command to find out what are the contents of A2. So reg is register, and core is 0 core and A2. So currently the contents is all zeros, and it should, if you observe over here, it's a 64-bit because we are running a 64-bit simulations over here. And then this particular command. So to do that, just press enter. If you press enter, it will run the next instruction. So the next instruction is LUI A201. So I'll explain what LUI means. What does LUI means? But let's find out the content of A2, and you will see it has got modified. So this instruction has been executed. What does LUI means? Load upper immediate. So I'll just walk you through this slide. It basically tells that if you have to load whatever the contents are over here, load the upper immediate, load this particular upper immediate of the register A0. So A0 is a 32-bit register, as you will be seeing very soon the list of 32 registers present in the RISC-V architecture. It will be covered in the coming slides. So the upper immediate is from bit number 12 to 31. That needs to be filled with whatever contents are present over here. So LUI A0, if it had been 01, so we have to fill the upper immediate from bit number 12 to 31 by 01. Let's map that to the lab. So when you say LUI A201, the upper immediate, so this is bit number 0 to 3, 4 to 7, 8 to 11, and 12 to 31, and then these are appended by zeros because it's a 64-bit architecture which we are running. So it has appended the upper bits number 12 to 31 by 01. Okay, let's look into the next instruction. What it does is load upper immediate of A0 by 0 to 1. So press enter. It will run the next instruction, which is this one, and now reg 0 A0 So from bit number 12 to 31, it's been loaded by 21. Okay. Let's look into the next instruction, which is this one. So press enter, and the next instruction that it ran was ADDI SPI SP 16. So in that case, I think we should have looked into what was the content of the stack pointer before, but nonetheless, so whatever was the content of the stack pointer before, it got updated. The negative 16, which is negative 10 in hexadecimal. You can go to the calculator. You can see if 16 in decimal is 10 in hexadecimal. So that number got subtracted from the initial value of the register pointer. Now that we have we know that we have to go back and look into the stack pointer register before running the instruction which is there on address 100B8. So let's do that. Let's do this. We'll quickly quit. We'll run the same command until PC 0 to 100B8. Okay, and then look into the stack pointer register. So initially the stack pointer register is 7F7E9B50, and after you run the ADDI command, now let's look into the stack pointer register, and you will see that hexadecimal 10 got subtracted from this one. So this minus hexadecimal 10 will give you 40. You can verify in calculator. Let's say 7F7. Let's do that. 7. Oh, we have to go to the hexadecimal. Clear of everything. 7F7E9B50 minus 16 in hexadecimal. If you put over here, just put 16, which is hexadecimal 10, as you see over here, and you will get the value in hexadecimal is 7F7E 9B40. So it matches. Okay, and what does this ADDI do? It's pretty simple. So ADDI basically, again, these are something which you are going to learn in the upcoming slides. So ADDI is basically add immediate. This is the destination register. So in our case it was SP. This is the source register, which was again SP, and it added the contents of the source register and the immediate and stored the content to the destination register. Okay, you might want to look into it's an ITAP instruction, and this is the architecture for the same. And if you're interested, you can continue doing the lab and solve the MCQs based on this particular lab, and we will be having some questions based on this lab. Okay, thank you.